Okay, just a second. Okay, we can start.
Hello, everyone. It's a pleasure to introduce today Professor Bill Harris from the McMaster University in Ontario, Canada. Bill obtained his PhD at the University of Toronto and was then a postdoc at Yale University. He has spent academic leaves in several places around the globe, including the Royal Observatory in Edinburgh, the Hertzsprung Institute of Astrophysics, at Kitt Peak, Mount Stromlo, and ESO. Bill is a member of the Royal Society of Canada since 2004 and has contributed a lot to the professional astronomy community in Canada and the United States. Most of you watching the seminar today will probably recognize him as the face behind the very useful Harris Catalog of Milky Way globular clusters, which has had a few editions since '96. But apparently over 20 years, random strangers have told him he looks like Donald Sutherland. Bill will be talking to us about his latest work on dark matter fractions in galaxies. Thank you so much, Bill, for accepting our invitation. You may start when you're ready.
Thank you very much. Greetings, everybody, and I'm glad to have the chance to speak to you about this topic regarding measuring dark matter in galaxies. So, dark matter is a dominant feature of work on galaxies and cosmology. And what I'm going to do today is to say a little bit about a relatively new way to measure the dark matter mass fraction within a given radius. I'm mentioning 5 effective radii for a galaxy as one particular case, but it's a more general thing than that. The work that I'm going to describe here today, it's in collaboration with a small group of others that are listed there on the page. Rhea Silvia Remus in Munich is a theoretician, runs galaxy simulations. Gretchen Harris at University of Waterloo, another optical astronomy professor. Yuri Babik, who was at Waterloo and now is a postdoc at UC Irvine, and Brian McNamara, a senior X-ray astronomer at Waterloo. So dark matter. I'm not going to give any kind of review of dark matter because I think we all know how important it is within our field, but I just thought I would show this to you to start with. This is the first concept that I've been able to find about the existence of dark matter. Almost 200 years ago, Friedrich Bessel said this, that we have no reason to suppose that luminosity is a necessary property of cosmic bodies. The visibility of countless stars is no argument against the invisibility of countless others. So almost 200 years later, we can see Bessel's argument as essentially quite correct. So luminosity is not a necessary property of mass. And indeed, if dark matter has the dominance that we essentially know that it does, then luminosity is actually a rather rare property of mass. So, okay, I'm going to talk, for a measurement tool, I'm going to use this, X-ray gas. This classic image is a Chandra X-ray satellite image of the gas, the high temperature gas filling the Perseus cluster of galaxies. The scale of this picture is about 1 megaparsec across, and you can see the incredible structure and substructure of the X-ray gas within its overall spherical, roughly spherically symmetric distribution in the potential well of the Perseus cluster. So this is gas on a very large scale, an entire cluster of galaxies, and it's centered on NGC 1275, which is the central BCG in the Perseus cluster, and an example of an extremely active massive galaxy, which has a central supermassive black hole and is pouring out energy at all wavelengths and so on. So this is a highly active galaxy in the center there, which is keeping this X-ray gas at a high temperature as energy flows outward. On a smaller scale, however, X-ray halos can also be found in large galaxies, individual galaxies. And here's a Chandra image of NGC 4649, which is one of the Virgo giant ellipticals. And now this is on a scale of many kiloparsecs, not a megaparsec. But again, you see the sort of smooth, symmetric contours of high temperature gas. And this is a feature of the baryonic mass in large galaxies that is reasonably common. Here are some other Chandra telescope images of other moderately big galaxies. Various degrees of signal to noise that you can see here, but again, it's not an unusual feature in large galaxies to see the presence of a halo of high temperature gas. And this gas is useful for quite a number of reasons. And one of the ways in which it's useful, which I'll explore today, is how you can turn that into a measurement tool to get the mass profile of any given galaxy in a way that's quite different from the normal kinematics and dynamics approaches. This all started a couple of years ago when our colleague Gretchen Harris had the idea that we could perhaps use this fact that large galaxies have X-ray halos to try to see how well those properties correlated with other indicators of the depth of the potential well for individual galaxies. So we published those results in a little paper last year, which just explored how global properties of the X-ray gas correlate with other indicators, including globular cluster populations of the total mass of a galaxy. So the graph on the left, here on the horizontal axis is the halo mass of a galaxy, which is essentially its virial mass, or its M200. That, of course, is dominated by dark matter, and more dominated as you get further away from the center of the galaxy. And on top, we've known for a few years now that halo mass correlates nearly linearly with the total mass in the globular cluster system of that galaxy. The different colors represent galaxies of different types, so ellipticals, disk galaxies, and SA types here in different colors, mostly ellipticals, as you see here in the red dots. And what you see here are the galaxies that have data for both globular cluster populations and the X-ray halos. And there are something like 50 or 60 of those in common. And that's the present state of things. Also a good correlation of halo mass and the total amount of mass in the X-ray gas, though not quite as close as the graph on top. And a nice correlation between the halo mass and the total gravitating mass within 5 effective radii. That's what this last quantity is here. Nice correlation, but not linear. The mass within 5 effective radii goes essentially like the halo mass to the 0.5 power, as you see right there, if you can read that. Over here on the right are 2 other indicators. One other indicator. One is the X-ray gas temperature. That responds very directly to the depth of the potential well. And so for individual galaxies, the X-ray gas is cooler than it is at the scale of entire clusters of galaxies, because the potential well that it's in is not as massive. But you see here then, at the rate of 1 keV per 12 million Kelvin, that the gas within individual galaxy halos is at the level of just a few million degrees for X-rays, until you get down to very low mass galaxies that don't appear in these plots because the gas now is too cool to generate X-rays, and it would be more prominent in the ultraviolet, but those don't appear here. At the scale of entire clusters of galaxies, then we go on up to higher temperatures. But we're going to stick to individual galaxies now. Okay. The dark matter mass fraction within a given radius r is useful. It is a direct measure of the relative dominance of dark matter at a given radius, so it's a function of radius. The dark matter mass fraction within radius r, by definition, is 1 minus the baryonic mass within radius r and the total mass within radius r. take that ratio, take 1 minus that ratio, and then you've got the dark matter mass fraction. So it's a simple definition. It will be a function of radius because dark matter is relatively more dominant at larger radii. But it's also an interesting potential tracer of the history, the evolutionary history of the halo. It can be modified by, for example, major mergers in the early evolution, which have the effect of ejecting baryonic material outward and then changing that ratio. It can be affected by adiabatic halo contraction of dark matter, which will change it in the opposite direction. Or it can be modified by episodes of expansion or feedback. So the possibility here is that you can use this ratio, which is a measurable ratio, to then work backwards and understand a bit more about the evolutionary history of the individual galaxy, particularly at early times when things were happening rather rapidly and the mass profile was changing in a more major way. So the central idea that I'll show here is just this. You get the baryonic mass here from the known stellar luminosity and from the mass in the X-ray gas too. You get the total mass within radius r, this number here, from the temperature and density of the X-ray gas itself, in a way which we'll look at in just a moment. And from those two measured numbers, you can then just calculate the dark matter mass fraction. And for the moment, for now, I'm just going to concentrate on a fiducial radius of 5 effective radii. And that's a fairly useful radius. Here's what 5 effective radii looks like for a typical large galaxy. This is another one of the major ellipticals in the Virgo cluster. The effective radius of the galaxy light is about 7 kiloparsecs, and so 5 RE is 35 kpc. So that circle encloses typically about 90% of the total stellar light. It's a large enough radius to include almost all of the baryonic matter, the light plus the X-ray gas as well, but it's still far smaller than the virial radius or M200, R200 by at least an order of magnitude. So it's not far enough out that dark matter is utterly dominant. So it's a radius that encloses a lot of the evolutionary activity that a galaxy has had, but it's not so small down at one effective radius, say, that it gets confused by all kinds of non-equilibrium processes that are raging away in the center. So it has some advantages. And in the recent literature, it's become a fairly standard radius to refer to. You can make analytical predictions, kind of back of the envelope predictions here. You could imagine modeling a galaxy in a simple way by saying that it follows a Hernquist profile or perhaps a Sarasich profile for the galaxy light. The dark matter would follow an NFW type of profile. You could imagine as a kind of numerical exercise to combine those two things and then calculate how the dark matter mass fraction changes with radius. And that will also change systematically with the total mass, stellar mass of the galaxy here, because the parameters of the Hernquist model or the Sarasich model and the parameters of the NFW model depend themselves on galaxy mass. And so you could expect a bit of a dependence of the dark matter mass fraction. Here's a rough prediction from a paper by Deason et al. In 2012. For the mass fraction within one effective radius, which shows a big increase with stellar mass. Dark matter is relatively more important for bigger galaxies, but a smaller increase for galaxies out at 5 effective radii, where you're already out partially into the realm where dark matter has become dominant. And when you try to match that with observations, Deason et al. Did that in 2012 when they wrote this up. They compared it with the available data for mass measurements within 5 effective radii. These data points are from globular cluster systems inside this set of about 24 galaxies. And they found reasonably good agreement. These are results for two different assumptions about the initial mass function for stars. The salpeter mass function concentrates more mass into lower mass stars, and so it actually increases the baryonic mass fraction, notably compared with the Chabrier or Krupa mass function that's a little more popular now. Okay, so that's where the situation was a few years ago. I will say something briefly about the so-called beta model that describes the X-ray gas itself. I am not an X-ray astronomer originally, so I had to learn about this for myself. And it started back in the 1970s. It has a long history. And at that time, it was discovered that X-ray gas was very prominent in large clusters of galaxies, and that the gas density followed a profile that looked like this. It's power law, essentially with an index -3 beta over 2, and it had a core radius R0. And this has been used since the 1970s, which doesn't really tell you why that index. Why is it 3 beta over 2? Why does the power law have this form, R over R naught squared, and so on? And you have to go back to these early papers to find out. But basically, the starting point is a very simple one. It's just the equation of hydrostatic equilibrium. For the X-ray gas, the inward pole of gravity is balanced by the pressure gradient, not by the gas pressure, but by the pressure gradient. And for clusters of galaxies, you can write the same equation down for either the X-ray gas or for the galaxies themselves that you can think of as point masses that are circulating in the gravitational potential. So if you take this equation, divide through by the density, then you can write down 1 over rho for the gas, dp dr for the gas, is equal to minus gm over r squared. And the same equation for the galaxies. However, now you can put in the expression for gas pressure, which follows the perfect gas law with a given density and temperature. For the galaxies, they follow an equation of state as a bunch of point masses with a velocity dispersion sigma v that looks like this. So if you put those two things in there and do a bit of algebra, then you get this relation, and move all the constants to one side. And what you find then is that under these assumptions, the gas density goes like the density of galaxies to the power beta, where beta is the ratio of these constants. It's the velocity dispersion divided by the temperature, essentially. The velocity dispersion of the galaxies divided by the gas temperature with some constants. And so that factor beta is the ratio of specific energies. The mean kinetic energy per particle is sigma squared over 2 for the galaxies. The mean kinetic energy per particle is, for the gas, is 3 kT over 2 mu h. Mu is the mean molecular weight. And so beta is just this ratio of constants. That's half of the argument. The other half is to use the fact that the galaxies follow an observed density distribution that looks very much like this. This was what people adopted back in the 1970s when this was first being put together. It's an empirical fit with a simple power law with a core radius R0 to the -3/2. So since the gas density goes like the galaxy density to the beta, there's where your extra factor of beta comes in, and there's your beta model for the X-ray gas. And if you want to see more of this, or it's unfamiliar to you, then I recommend this nice paper, now more than 40 years ago, but it's got exactly this nice derivation that gives you all of this. And this is the way things have been done in the field since then. When we shift now to X-ray gas within individual galaxies, then the same formalism has been borrowed. Instead of talking about galaxies within a galaxy cluster, now we're talking about stars within one galaxy. And For clusters of galaxies, the beta ratio is about 1 because both the gas and the galaxies are following the same dark matter potential well in the same way, really. For individual galaxies, beta is different. It's more like about a half. But that's fine. In either case, you can turn the equation of hydrostatic equilibrium, which is our starting point, into a simple expression for the total mass within radius r. Here it is. And do a bit more algebra. And at large radius, that just reduces to a bunch of constants times beta times the X-ray temperature times the radius, which is incredibly simple. But it gives us a way to determine the mass profiles of galaxies that's nearly independent of the more well-known satellite velocity technique that uses things like globular clusters or planetary nebulae or halo stars or dwarf satellites and so forth. And in astronomy, having more than one way to measure a given quantity or a given goal is a very good thing. So we realized that in our first paper, and we found that for the sample of galaxies we had, we could generate this graph here. We've now used the X-ray halo light in the galaxies that you saw on the previous graph to plot up the dark matter mass fraction within 5 RE and plot that against stellar mass. And this is the distribution that we got. Again, it's color-coded by morphological type. And you see that around 80%, at 5 RE, about 80% of the mass is now dark matter. And there are deviations, of course, and there is scatter. Certainly, some of it is simply internal measurement scatter, as you can see from the error bars. Some of it likely to be real, though, and to reflect individual differences between galaxies in terms of their histories. The theoretically expected range, here we didn't refer to analytical models, but went right to a suite of simulations, the Magneticum Pathfinder simulations. And as long as those simulations include both the stars and the gas, they can be used to predict and to generate graphs like this for the individual galaxies in that simulation suite. So this gives us a route into comparing current theory or current suites of simulations with observations. Again, in a way that's different from just using the dynamics of halo satellites. It's quite a different approach to it. Another word about the Magneticum Pathfinder simulations that are being used here. All the details can be found on their website here, but they are a series of runs of cosmological hydrodynamic runs for galaxy formation. They have a range of box sizes and resolutions. They're all built on standard lambda CDM parameters. The two major ones we'll be looking at here are the so-called run concentrating on normal galaxies. It has a smaller box width of 48 over H megaparsecs. And for stars, it has a resolution scale of 2^10⁶ over H solar masses. And then a separate run for central giant galaxies, BCGs, things like that. Those were extracted from a larger scale run. And you can see here, the resolution is about an order of magnitude larger than it was for the normals run. And here's just an illustration of one such run, which shows that you can extract individual galaxies with disk types over here and early types over here. You have the full range. Here's one example showing a large cluster that emerged from this particular run, which has a central BCG, the gas contours as well. The distributions of mass density and gas density shown here. So this is relatively recent work, and that group is developing as it goes. Okay, here are some results now. This is in a new paper that we have submitted, and it's under review right now. And now we have to be a little more careful what we mean by the dark matter mass fraction. This is the mass fraction within 5 effective radii. It's 1 minus the baryonic mass divided by the total mass within 5 RE. The baryonic mass now includes the stellar mass and the X-ray halo gas mass itself. but it's not the entire stellar mass, it's the mass fraction within 5Re. And so that's the mass fraction ratio Q here, and that's about 90%, so that's about 0.9. Mx normally is quite a bit smaller than M star, and so the stellar mass is still the dominant part of this numerator here. The total mass within 5Re is then what we're measuring from the distribution of density and temperature of the X-ray gas itself. These two graphs really say the same thing. One plots the dark matter mass fraction versus halo mass or virial mass, and the other plots the same thing versus stellar mass. And since they say about the same thing, I'm just going to show the graphs versus stellar mass in the next slides. The red dots are the theoretical simulated normal galaxies. The green dots are a large bunch of centrals or central giants. And the data points, the black dots, are a sample of just about 100 galaxies with Chandra X-ray profiles that are good enough for this purpose. And you can see here, okay, the bulk of the points are around about 80–85% dark matter fraction, and they're in the same range as the simulations, perhaps a little higher on average. But it would be hard to say that that's definitely because the simulations are wrong, or definitely because there's something wrong with the observations. Down at this level, there's probably not enough precision in either one of these to say if there's a problem there or not. But to first order, they're in pretty good agreement. There's a string of objects up here that's pretty obvious. And then there's a scatter of objects that go down here that are pretty obvious. And I'll say more about each of those in a minute. Here are the same galaxies broken by morphological type. On the left, you see here the ellipticals in black and the disk galaxies in orange. And you can see here, in fact, this string of objects that sits up at quite high FDM. They're all disk galaxies, and they're all relatively lower luminosity compared with the average of the others. And so these appear to be disk galaxies with very sparse stellar halos. They don't have they don't have much in the way of stellar mass at large radius, which would bring this ratio down. So it appears, I mean, on the surface, the nominal interpretation would be that these are galaxies which have had a very quiet history, nothing in the way of major mergers or interactions or feedback, which would have pushed a lot of stellar material out to the outer halo, and which would have the effect of bringing this mass fraction down. These points down here, and in particular the lowest ones, have unusually high values of the X-ray gas mass, which would drag the dark matter mass fraction down. And those are probably a mistake. Those are probably observational uncertainty. And I'll talk more about which way the observational uncertainties work later as well. But now, on the right-hand graph, they're broken out by normal versus central, essentially. Early type galaxies in black and central giants in the open symbols. And there's not too much difference systematically between them. The normals and the centrals are both behaving in much the same way in the same mass range. Okay then, we do have this other method for measuring dark matter mass fraction, which is more classic, which is to use the satellite dynamics and kinematics of things like globular clusters or planetary nebulae. What about a comparison? And so that's what this graph is showing you. Are those two methods, X-ray halo versus satellite dynamics, telling us the same thing? And by and large, they do. The blue dots here, the new set of dots, are data taken from a comprehensive paper by Alabi et al. Published in 2017, where they used the kinematics of globular cluster systems and planetary nebulae in this set of about three dozen galaxies or so, in a homogeneous way to measure the dark matter mass fraction and the mass profiles. And so that's what those points show. And by and large, they overlap with the X-ray halo data rather well. The shaded area, this area that runs through here, in fact, is satellite kinematics measurements in a different way. This is data from Wojtak and Mammon in 2014, where they used a set of a few thousand galaxies selected from the Sloan Digital Sky Survey. They're individual large galaxies that are moderately isolated, but which have a few dwarf satellite galaxies in each case. And what they've done is simply to take bins of galaxies in different mass ranges, here and here, and here and here, and so on, and bin all these galaxies in that mass range together and get a mean mass ratio and therefore a dark matter mass fraction at 5 RE. And again, by and large, to first order, it's sitting at the same level, about 80 to 85%, but it does have this very interesting dip that goes down to actually about 65% here at a stellar mass around 2 times 10 to the 11 solar masses. And that's curious. It doesn't show up in the simulations, but it does resemble to some extent the downward scatter of these individual data points that you see here. These you can probably ignore, but these are over in this range are probably real. Okay, all right, these methods are telling us more or less the same thing. But of course, both methods have problems. Any method that we use in astronomy is going to have problems. On the case of the satellite dynamics method, it's well known that you have to do something in terms of assuming features of the orbit anisotropy or lack of anisotropy. There are issues of sample size. If you're using, say, a set of globular clusters to measure a velocity dispersion in the halo, then your result might be dominated by the small number of clusters that appear at the largest radii, depending on the method that you're using. Orbit anisotropy continues to be a big issue because perhaps it's not even the same degree of anisotropy at a given radius as it is at another radius. For the X-ray profiles, there are problems as well. We have our inbuilt assumptions of spherical symmetry for the gas distribution. We've got the assumption of hydrostatic equilibrium. We've got details of the gas physics that may be oversimplified, and so on. You can take each one of those methods and really criticize it if you want. But the point is that these biases and problems are different in the two methods. They're quite different. And so with all their faults, we actually do have something close to genuinely independent methods that we are comparing one against the other. And there are a few overlapping cases. Some of the galaxies in each data set overlap with galaxies in the other data set. And what about those? And it turns out those actually agree encouragingly. This is the difference in F5 versus stellar mass for galaxies that have measurements on both the X-ray side and the satellite dynamics side. And you see here the scatter gets worse at lower mass, but of course it does. At lower mass, you have smaller numbers of satellites, you have lower X-ray luminosity and lower temperature. And so for any method, either of the methods, the difficulty is greater here at lower mass. At higher mass, the agreement is pretty good. It's as good as we could have expected going into this. And now just a word about how we end up with very large or very small F5. You see here in the simulations, the normals and the centrals, they follow very similar distributions, centered near 0.8, with not much in the way of lower values, very few going down to lower values. The measurements, the X-ray disk types here, the E types here, the satellites here, they have more of a noticeable tail going down to low F5. Well, you can get differences, either increases or decreases in F5 due to major events like adiabatic contraction of the halo, which would bring in dark matter to the inner halo and therefore increase the dark matter fraction. You can have major feedback, such as AGN activity or mergers, which will bring baryonic material outward, and you can use that to decrease the dark matter mass fraction by surprising amounts. But values less than 0.5 are quite rare in the simulations, and probably a bit of an issue for the observations. So the observational uncertainty is actually, when you look at this equation here, it's mostly due to the uncertainty in the measurement of the total mass. The baryonic mass here is more well understood usually, and it's a small number anyway compared with the total mass. And so this is usually the dominant source of the uncertainty. If you overestimate the total mass, that's not so important because it was already large compared with the numerator. So if you make it a bit larger, that doesn't actually change F5 all that much. If you underestimate the total mass here, that can have a big effect on F5. It can make it quite a bit lower. And that is probably the sort of asymmetric tail here that we're looking at. Another effect that will go in, as I mentioned earlier, is that you can, if you overestimate the X-ray gas mass, that can also decrease F5 quite a bit. If you underestimate it, it's not important because this is already usually dominant. So there's a kind of subtle interplay of the way observational uncertainties enter into the results here that probably means we need a larger sample of galaxies to fully understand. So again, the galaxies down here are precisely ones that have unusually big values of MX, the X-ray gas measurement, and we believe that those are observationally overestimated. And that if you remove the MX value, then all these points move up right into here. They join the main group of points. Some of you may have been wondering about gravitational lensing. There is another way to measure gas or sort of galaxy masses, which is lensing. And so I've done one more thing here to this graph. First of all, knowing that the satellite method and the X-ray method actually agree mutually pretty well, then it's fair to average them up. And so what we've done here is to combine all the data, the X-ray data and the satellite data together into 117 nearby galaxies in total, and then divide them into bins by mass. And so those are the mean points that you see here, the black dots with error bars. And those follow the Sloan data, the shaded regions, reasonably well. And in particular, if you look at this dip, it might be that what we're looking at in this dip is it's not so much a change in the median value as it is the presence of the outliers that go down to low mass. And perhaps those are in the Sloan data as well. And they were not really spotted as such because they were binning things right from the start. But the mean value for the measurements continues to sit a little high compared with the models, compared to the simulations down here in this range. These are the normal galaxies, simulated galaxies in red, their mean points, and the central galaxies in green here, their mean points by mass bin. And so they do tend to offset to the simulations here by 5 to 10%. And that probably is something that needs to be looked at in future rounds of simulations and what goes into them. The new thing on this graph really is that horizontal line. It's this line right here. There are, in a paper published in 2014, there's a list of 161 galaxies measured via strong lensing that are relatively nearby, the SLAC survey and others. And they're not plotted versus mass, but when you bin them all up, they give a mean F5 value of 0.86, which again sits a little high relative to the simulations in particular. And it sits a little high compared with our measurement data in this mass range. But again, within the range of about 5%, they're telling us the same thing. So we have first order agreement in 3 fundamentally different methods: strong lensing, X-ray halo light, and satellite kinematics, which is encouraging, at least that we're on more or less the right track. That little dip, it may also be connected, of course, to the peak in the stellar to halo mass ratio, the ratio of stellar mass to halo mass, which reaches a peak around 10 to the 11th solar masses, because that's the mass at which feedback is least important. At higher masses, you have feedback due to AGNs. At lower masses, you have feedback due to supernovae, which become dominant and prevent a lot of the initial gas from forming stars. But this is the mass range where stellar formation was the most efficient. Maybe that's connected. That's a bit speculative at this point. We don't know. So finally, what about the future of this subject? It probably has occurred to you that picking a fiducial radius of 5 effective radii is a little bit arbitrary. It's been done frequently in the literature for the past 10 years or so, but there's no necessity to restrict ourselves to 5 RE. We can go beyond that to asking what the dark matter mass fraction is at many different effective radii, and therefore build up a mass profile if we have a good measurement technique that works at a lot of different radii. So here is the dark matter mass fraction as a function of radius for all those simulated galaxies in the Magneticum Pathfinder simulations. And you see here they define a whole family of kind of S-shaped curves where the dark matter mass fraction is small at small radii, and then of course it curves down to, you know, asymptotically high value at very large radii. And all we've got are these data points here at 5 effective radii, that are lined up here at 5 RE, and this is where they are. But we have promise here that for particularly good observational cases, we can take a given galaxy, develop an entire curve like this, fit it on to wherever it lies on this suite of simulations, and then help us to read off the individual history of major episodes of merging or feedback, star formation, and so on for that galaxy in a way that's different from other approaches that are in the literature. So we're gathering data of that type, picking kind of the best galaxies in this sample of objects, and that work is currently underway. But that is where I'll stop for today. Thank you very much.
Thank you very much for your talk, Bill. For the people following the talk on YouTube, thank you for joining us. If you have any questions, please post them in the YouTube channel.